Happy Friday, y'all. So we're going to be finishing the thermal chapter up by talking about the various technologies that could consist of a thermal control subsystem. So we've used this diagram many times already. It's the New Horizons thermal subsystem with the different components broken out. And I hope that by the end of this lecture, you'll be able to regurgitate what a radiator does, what a thermal shield does, what these RTG thermally isolated mounts and shunts, what all of these different components do, and maybe why they are mounted in the way that they are. So we'll survey mechanisms used in spacecraft to achieve these thermal interactions. Before we go into the specific technologies, I think it's useful to think about thermal control in two categories. There are passive solutions and there are active solutions. So for passive solutions, we've got using different materials and surface coatings. And then we've got heat shunts and straps, heat pipes, heat sinks and radiators, insulation, and radioisotope heater units. And then for active components, those that take in electricity or intelligence, both at once, we have heaters, louvers, I actually don't know how to say this, louvers, pumped fluid loops, and cryocoolers. So before we start, there was a question generally, would the passive technologies be optimal forms of engineering for your project to require less strain on resources? And I'd say that there's a trade-off. I think certainly passive solutions don't take up power, but they can be quite massive solutions. Like maybe you need a huge radiator to get rid of heat from this one component, whereas maybe you can use a small cryo cooler that has a cold tip just to do a focused cooling of this component. So it's really a trade-off. The advantages of passive solutions are that they are simpler, which is great for mission operations, and also for mission risk. They don't take up power, but active solutions can be that you have more refined control, more targeted control. Yeah, so it's always a design decision when you think about designing any part of the spacecraft. It's nuanced. So let's go into passive solutions. We've covered materials and coatings when we talked about absorptivity and emissivity. And there's just one concept that I want to clear up. I don't think I explained this well last time when we were going over the fundamentals of heat transfer. But so alpha, absorptivity, and epsilon, emissivity, they vary from 0 to 1, where 0 is very minimal heat transfer and 1 is a lot of heat transfer. So the absolute value that these have matter. Those close to 0 are going to be more insulative, and those closer to 1 are going to be more conductive. And these can vary between 0 and 1 for both absorptivity and emissivity. Now, the ratio is a relative concept. So despite this ratio of 3 being in favor of absorbing more than transmitting, you're still not going to have that much absolute heat transfer because these numbers are quite low. Whereas, yeah, something that has a ratio of 3, but has an absorptivity of 1 and an emissivity of 0.33 is going to behave in a much different way. You would have much more heat transfer. So I hope that cleared it up. There are just 3 numbers that are important. You have to consider all 3, not just the ratio. All right, so back to materials and coatings. The technologies that are typically used for materials and coatings, well, the materials can be a a solid, a bulk material with a different property, and different structural components or just different physical components can be made out of this material. Whereas coatings differ in that you have the bulk material that's underneath, and coatings are a surface layer. So if we look at how coatings work, you can have incoming radiation, and the coating layer rejects some and can penetrate the layer a little bit as well. You can see this kind of manifested in this technology that Youngquist developed at Kennedy Space Center. So here he's taken salt. You can take table salt and then grind it to a very, very fine diameter and then press it into a powder. By doing so, he's proven that by coating your spacecraft with this very fine packed salt, you can get a surface coating that brings the spacecraft in low Earth orbit to cryogenic temperatures. So the inside of the spacecraft can get to like 100 degrees Kelvin, which is negative 173 Celsius. Don't quote me on the exact number, but cryogenic is around that regime of temperature range. Now that's incredible. That's a passive solution. So that can show you kind of the power of using a state-of-the-art surface coating. Let's see, I guess, so yeah, table salt. This picture shows how reflective the surface coating can be. And that's kind of how this, how the coatings work. Last time, we were talking about how polished aluminum behaves differently than anodized aluminum, which answers this question of, do anodized materials also affect the thermal absorptivity and emissivity? Absolutely. Okay, heat shunts and straps. Heat shunts and straps are used when heat, thermal energy, needs to be transferred and a large temperature gradient cannot be tolerated between two or more discrete locations. So these heat shunts and straps are attached to point-to-point end connections in which you want to transfer a hot spot to, or heat from a hot spot to a cold spot. You typically see these on a lot of electronics. And you can see here a thermal image of a shunt, a heat shunt, under load conditions. So when we use it on ground, we rely a lot on convection. So you'll see here that there's a lot of surface area that's exposed to potentially flowing air, but in space we need to remember that there isn't that convection. This would just be subject to conduction, which is the dominant force, and radiation. Now, heat shunts and straps, you can toggle the material that you make them out of. So here I have different thermal conductivities that govern how much heat transfer can be shunted across a strap or a shunt. You'll see here that aluminum, which we're very familiar with, and copper, which we're very familiar with for electronics, have probably the lower end of the spectrum when it comes to how thermally conductive you can get, whereas graphite fiber and other forms of graphene, graphite, have much higher thermal conductivities. And then there are a wide array of potential applications for thermal straps. Let's just look at the aerospace end of the applications. So for very cold applications, we could see heat shunts and straps used for infrared and X-ray science. Remember, optics are quite thermally sensitive and want to be quite cold. We'll see heat shunts and straps used for cryo coolers, for stored cryogens, for sensors and detectors. Now, for less thermally stringent scenarios where you could maybe just be cold instead of very cold. You'll see heat shunts and strategies for radiators, electro-optics, telescopes, thermal shields, cryocoolers. And then for ambient conditions, we can think about them being used in cryocooler compressors, vibration isolation, deployable systems, and radiators. So heat pipes. This is kind of like a heat shunt or strap, but instead of the material that is transferring the heat, instead of that being a bulk material, conductive material, you're using a fluid. So you're taking both conduction from the metal or whatever the bulk material is that's structural, and the fluid that is going within the pipe. So you'll see here is the bulk material, and then within that pipe is the fluid. So let's answer some of these questions. Why is ammonia used more commonly than other fluids? So last time we looked up the thermal conductivity of ammonia relative to water, and we saw that ammonia was 2 magnitudes higher in thermal conductivity than water. So that's just one reason. There are other reasons, such as ammonia being 10 to 20% less expensive than other CFCs. And CFCs are types of refrigerants. Ammonia is also more efficient refrigerant than CFCs, as in they require less electricity, and that could also lower, your power budget requirements. And on ground, lower operating costs. Ammonia is also safe for the environment. It is hazardous to work with, but there are warning signs when you're working with it as opposed to CFCs. Here is another question. Is there a minimum size for spacecraft to be able to put heat pipes on them? Would it be feasible to put these on a 1U CubeSat? Now, I don't typically see propellant systems or fluids like in heat pipes on CubeSats. I do think that the trend is for heat pipes to be in larger spacecraft systems like the ISS. That's not to say it's impossible to put fluids or heat pipes on spacecraft. I think that if you were to dedicate your CubeSat to have really hot electronics, and it necessitated the need for heat pipes for some convection, and conduction wasn't good enough, or radiation wasn't good enough, then it could be used. Never say never, but not common. All right, so heat sinks. Heat sinks transfer the heat generated by an electronic or mechanical device. This differs from the other things that we've seen, as the other mechanisms were point-to-point heat transfers, whereas a heat sink is more of a node, where, just as the title says, sink, you're trying to trap all the heat towards you. We see a lot of these on ground, on electronics, for mounted against like CPUs or other really, powerful electronics that needs to be cooled. So we see them typically paired with fans, with the use of convective forces. That's not to say you can't use it on a spacecraft. You can attach a radiator conductively to a heat sink to transfer energy. So the heat sink would be what you draw everything to. It could be a reservoir heat, and then the radiator would be your mechanism to radiate it away. Is it safe to assume that heat sinks probably don't work too well on small sats like ours because there isn't much space for an adequate heat sink? I mean, I think like the last question, I don't really see it that often in small spacecraft, but it's not to say that it never happens. Like I was talking about, there are common pairings. It would be intuitive to pair this with a radiator, but a radiator, you need a lot of surface area and thus mass. So it does make it more difficult to use in mass and volume constrained satellites like CubeSats. So I guess general trend, probably safe to assume that heat sinks aren't on your CubeSat, but you're a CubeSat designer, you should decide, does a heat sink make sense for the application I'm using? Radiators. So I just talked about radiators in the last slide, but to reiterate and to go more in depth, radiators reject heat by radiating from their surfaces. So there are two colored radiators that are on display here. There is a black radiator, which is being installed at the NASA Goddard Space Flight Center. There are also these white coated radiators on the ISS. So radiators use their surface area to eject heat into deep space. They scale with the amount of surface area that they have. And I guess it also matters what material you make it out of, because wherever this heat source is coming from, you can flow more heat across this surface area if your material is more conductive. All right, let's talk about insulation. Commonly, we see insulation in the form of MLI, which stands for multi-layer insulation. The layers of MLI are typically a reflective foil and then an insulating layer, and then you reiterate this pattern. Typically, you'll see the use of mylar as the reflective foil. Okay, so insulation works in the way that there's some incident radiation. A lot of that gets reflected away from that reflective foil, but what does get through to the next layer would get reflected away from that second reflective foil. The reason why there's an insulating layer is because if you had these reflective layers stacked directly on top of each other, then it would, in essence, react like a bulk material, as if these multiple layers were collapsed into a single layer. So to get the compounding effect of distinct layers, you have to have this insulating layer that separates the reflective foil. This spacecraft on the right is the Mars Reconnaissance Orbiter, and you can see that it's just covered in MLI. MLI is a very common solution, and you'll see not only the outside of spacecraft getting covered, but components on the inside also getting covered. There's another type of insulation. It's called aerogel, and it is a magical material. You'll see here that it is incredibly light, but it is also incredibly heat resistant. There are pictures where there is a flame underneath, and there is like a flower on top that is totally happy sitting there, although there's just like a flamethrower underneath. It's a synthetic porous ultralight material derived from a gel, in which the liquid component for the gel has been replaced with a gas without significant collapse of the gel structure. The result is a solid with extremely low density and extremely low thermal conductivity. In this picture, you'll see NASA used an aerogel to trap space dust particles aboard the Stardust mission. These particles vaporize on impact with solids and pass through the gases, but can be trapped in aerogels. NASA also used aerogel for thermal insulation on the Mars rover. Yeah, so that's a really neat material. So the last passive technology I'll talk about is the radioisotope heater units. These are like RTGs, but instead of converting the heat into useful electricity. All of the functionality is just dedicated to heat generation. They do so through radioactive decay. So here you'll see an anatomy of a radioisotope heater unit. Essentially, it is some radioactive material as a core. They're typically in the form of pellets, and there's a ton of insulation. Yeah, and a heat shield. But these are supposed to toggle the amount of heat that's going through. And it could act as a radiation shield. RHUs are used in a ton of missions. So these panels, you'll see there's Galileo, there's the Huygens probe, and on the two MERS, so Opportunity and Spirit, RHUs were on board. RHUs give off heat continuously, somewhere between several decades and up to centuries, given the gradual degradation of the radioactive isotope. So all of the other passive solutions that we talked about, they're about heat transfer and heat sink. This would be a heat source. It's like the last part of the solution to get a full suite of solutions. Generation, transfer, and emission. So a question, how is it determined exactly how many RHUs a spacecraft will need? Is the RHU completely, okay, so the first question, how is it determined exactly how many RHUs a spacecraft will need? So I think it doesn't necessarily require us to say how many RHUs, but how much thermal energy, how much warmth do we need to generate for a spacecraft? And so typically, regardless of the technology, we do a thermal analysis to see if the spacecraft as a whole and in spots at different components, if it runs hot or cold. In this case, since we're looking at a heater, we're looking at spots where the spacecraft is running cold. We can do that by, you've been, or you will collate the operating temperatures of the different components that are on board the spacecraft. And then you can, once you have your components configured in some geometry, then you can run a thermal analysis and probe the cold spots, see if all the components will survive. So that's generally how you determine how many RHUs. Specifically to an RHU, they're tested, characterized with the amount of heat that they give off at a constant rate. So I guess divide the amount of heat that you need in your spacecraft with the heat per unit of RHU, and then given that ratio, you know how many RHUs your spacecraft will need. The next question, is the RHU completely isolated from the rest of the spacecraft in a shielded compartment and only allowed to transmit its heat through conduction? If not, must all the other parts of the spacecraft be engineered to withstand low levels of radiation? It's actually a good question that I did not look up because it's more nuanced. So I think conduction is certainly a way that the RHU can transfer heat. Now, when it comes to heat radiation, given that this RHU is going to be warmer than the rest of the body, there is definitely going to be some kind of radiation. The heat is emitted at infrared. When it comes to this other type of radiation, must all the other parts of the spacecraft be engineered to withstand low levels of radiation? I think what you're talking about is high energy radiation, which is dangerous for electronics. So if the shielding can mitigate high energy particles from escaping, that's great. For the other wavelengths of radiation, it can come out of this container and the electronics would theoretically be safe. So not only conduction, but also radiation, but just be specific about what kind of radiation. Okay, active. And it's nearly half the hour, so I'm running behind. Sorry, everyone. All right, so active components, heaters, convert electrical energy to thermal energy. So I have here two different geometries of heaters. They all will have lead wires, some positive and some ground. And they will, so that's the transfer of electrical energy. And then there are mechanisms within that convert the electrical energy to thermal energy. Now, this cylindrical heater, it's a cartridge heater. And typically the way that it is used, it's slotted into a component that needs to be warm. So this would be at the core. Here on the right, the heater is a flat heater. So it works well on surfaces. For example, on the Artemis CubeSat kit, this is the heater that we're going to use, and we're going to put it on top of the battery pack to keep it warm. Now, a heater, it doesn't always need to be on. You can toggle how much heat is emitted from the heater with the amount of current, voltage that you pass through. So what else do I want to say? No, that's good enough. Louvers. Okay, so louvers toggle heat transfer by scaling the exposure to space. There is some surface underneath this shuttered window, I would say, and this surface has an amount of heat. Now, remember we were talking about multi-layer insulation? You can think of this top layer being that surface layer, but you can toggle whether it's, creating a cohesive surface or whether it's this porous surface. If it were a cohesive surface, then it would act as a layer and it would insulate. Whereas if you adjust these little shutters, you're pretty much scaling the amount of surface layer actually exists to insulate. So you can have a variable control of how much surface is getting exposed and getting radiated out of that behind surface, that back surface. You can see them being used here underneath the New Horizons spacecraft. You'll see these little window shutters. I should have used resembling Venetian blinds. That is a much better way to describe them. As a rule of thumb, louvers reject 6 times as much heat in the open positions as it does in the closed position. I guess this would be kind of an alternative to the surface coatings, which have that absorptivity to emissivity ratio. Just another solution. Okay. Pumped fluid loops. We have seen this picture before on the ISS. So the difference between the heat pipes and the pumped fluid loops is that a heat pipe is totally passive, whereas these pumped fluid loops rely on this pump, which is an active component. The pump acts to circulate a working fluid, transferring heat between the different heat sources to the fluid to eventually a radiator. Yeah, I feel like it's pretty intuitive, and I guess we don't really use it in CubeSats that often. I've never seen it, but maybe if you work on a larger spacecraft, it'll be more relevant. Okay, so cryocoolers. I do want to spend a little bit of time on cryocoolers because the state of the art for cryocoolers has gotten small enough that we can put them in CubeSats. In fact, there's going to be one in HiTi, which is an HSFL mission. So cryocoolers are refrigerators that reach cryogenic temperatures. The way that they work is the way that they work is they have a compressor. They also have heat exchangers, and I've usually seen some cryogenic fluids like liquid helium. But anyway, through a series of compressing and condensation, you can get very low temperatures to the cold finger. You're concentrating all of your heat rejection. You're trying to take as much heat, displacing it away from this focused area. So yeah, you're like circulating this cryogenic fluid, rejecting as much as you can away from this area, and you focus it away, probably like there's going to be some kind of heat sink and heat transfer away from that cold finger. I didn't do a great job explaining it, but what you're going to see is this fingertip, this cold finger, that's going to be very cold, and that's mounted to your payload, your instruments, your optics, and then you'll probably get a bunch of excess heat. Like any refrigerator, there is a focus spot where you want it to be cold. You need to displace the heat that's within this volume, and then that heat gets concentrated in other areas. The back of your refrigerator, underneath your refrigerator, are going to be very hot, not only from the heat displaced from the volume inside, but also the heat needed to do the displacement, do the work. Okay, here is a technology setup of a cryocooler. There are cryocoolers that are half a U. So imagine your little 1U CubeSat, about half of that volume is dedicated to a cryocooler. A lot of advances have come from the military to cool optics in night vision goggles. So, you know, night vision goggles, infrared wavelengths. To do that, to see that, you need very cool optics. So you can put cryocoolers that fit on your goggles. It's really neat. Okay, so done with our survey of the different thermal control technologies that are out there. Hopefully by now, you will be able to understand, oh, what is MLI? What's its purpose doing there? And radiators, what's its purpose? Louvers, is this spot more, variable between hot and cold, which is why we need to control it, whereas radiators, we need constant emission all the time. So there ends our thermal control chapter. Great.